Okay, so today we're going to look at a simple law of gases, one of our first laws, called Dalton's law of partial pressure. And this is the scenario that we use to kind of explain how this works. And a lot of times in industry or in labs that study gases, it's difficult to produce a gas and then collect it. You know, if you just try to release it into the atmosphere, you're never going to be able to catch it. But a really easy way to harvest the gas that you've collected is to do it in what's called a water trap. That's this guy right here. This big piece of apparatus is called a water trap. And what happens is your reaction produces a gas, and it's this kind of pale yellow color, this gas. And it just as it's produced, it travels through this apparatus and gets released under the water in this water trap. But they make sure that the opening of the apparatus is beneath an inverted test tube. And so what happens is as the gas is produced, it gets collected in this space above the water. And it's totally isolated and it's not going anywhere. And then if you want, you can insert a valve right here and collect it later on. And the gas that is collected over the water in this test tube is totally pure. Or is it totally pure? So let's take a closer look at what this space above our water trap looks like, because most of the gas that we have collected most of the space above this water trap is the gas that we've collected, but there's something else. Let's look in a little closer. Okay, here's a bit more detail. Let's say that the reaction that we were using is a reaction that reacts zinc plus hydrochloric acid, and when you're done, you get zinc chloride and hydrogen gas. And here it is, traveling through our apparatus to our inverted vessel, and it gets released in the space over the water. And as a matter of fact, they'll fill this entire thing with water, and the gas, as it fills the space, actually pushes the water out. But look a little closer. It's not just hydrogen, because what happens is at the surface of the water inside the trap, that the water molecules themselves actually start to evaporate. And that means that whatever gas that we're collecting inside this water trap is going to be pure, except for the fact that it's going to have a little bit of water vapor inside. So when we're calculating the amount of gas that we collected, we need to subtract from it whatever water vapor we might have collected. And it's really easy to do, because the hotter the temperature, the greater the temperature of the room that we're in, the greater the tendency of our water to evaporate. And that, of course, is the tendency of water to evaporate. We're going to call that vapor pressure. Sorry that my ink is so big. Let's make that a little bit smaller so that you can read that. Vapor. Just vapor. Vapor pressure. And it's a function of temperature. So here's how we're going to do this. We're going to assume that on the outside of this trap is atmospheric pressure. And atmospheric pressure is whatever the pressure of the room or the atmosphere is in. And usually we're at standard sea level air pressure. So we'll say that this is 760 millimeters of mercury, or whatever that you want to use. We're going to say that because the pressure outside the trap is 760 millimeters of mercury, and we're going to say that once we stop producing our gas, that the level of water in the trap stops moving. That means that the pressure inside this trap has to be equal to the air pressure outside the trap. So we'll say that the air pressure inside is also 760 millimeters of mercury. So that means that we know that the total pressure inside the trap is the total sum pressure of all of the gases involved. Well, we made hydrogen and we also made water vapor. So let's take a look at how we're going to calculate this. So this is Dalton's law of partial pressure. And it says in words that the total pressure in a mixture of gases is the sum of the partial pressure of each gas. Meaning that if we have a vessel that contains some gas, the total pressure inside the vessel is going to be equal to the sum of all the gases that are inside the vessel. This will be in our trap or whatever. So if we know that in this water trap, our space inside the space above the trap contains both hydrogen and water vapor, that means that in this case, the total pressure inside the trap is equal to the partial pressure of the hydrogen plus the partial pressure of the water vapor. And because we know that the outside air pressure in the room is 760 millimeters of mercury, that means that the pressure inside the trap has also got to be 760 millimeters of mercury. And so that means that we could easily find the partial pressure of one of these gases if we knew the other. And what's neat about this particular phenomenon is that the partial pressure of water vapor is a function of temperature, because water evaporates. So the higher the temperature, the greater the tendency of water to want to evaporate, and the more water there will be in the space above the trap, and the higher the pressure of the water will be. So all we need is a way to find out what that is. That's where this table comes in handy. Check it out. It says vapor pressure of water, and it gives us two pieces of data. The first column is temperature, and the second is pressure in millimeters of mercury. And it tells us that, for example, at a temperature of 5 degrees Celsius, water would be exerting a vapor pressure of 6.5 millimeters of mercury. And the higher the temperature, the higher the vapor pressure. So at 25 degrees Celsius, there is a vapor pressure of 23.8. So let's see how we use this to solve a partial pressure problem. Say that 3 times fast. So this is the type of question that we're going to try to solve for this. It says, what is the partial pressure of hydrogen gas collected over water at 25 degrees Celsius if the room air pressure is 775 millimeters of mercury? So Dalton's law, as we've already seen, is that the total air pressure is equal to the sum of all of the individual gases that we are collecting. Well, we happen to know that the room air pressure is 775 millimeters of mercury. And that means that the total pressure inside the trap has to be the same. So that means that it is the sum total of the partial pressure of the hydrogen gas and the pressure of the water vapor. Well, all we need to do is find the water vapor pressure at 25 degrees Celsius, and we're golden, and that's already right up here in this table. So 23.8 millimeters of mercury. All we want to do is solve for pH 2, so that's easy enough. We're simply going to subtract 23.8 from both sides. So 775 millimeters of mercury minus 23.8 is our partial pressure of hydrogen gas. So just bust out your calculator. Some of you are good at math in your head. I am not. 775 minus 23.8. This gives us a partial pressure of our hydrogen gas of 751.2 millimeters of mercury. And that's all that you do. So take it for a spin, and I'll see you on the next one.